Hi, everybody, and welcome to the August EERI Younger Members Committee webinar titled Advances in Seismic Risk Assessment Using Simulated Earthquake Ground Motions. My name is Amanda Sullivan, and I'm a structural engineer at Bureau Happold in the New York City office, and I'll be moderating today's webinar. Before we start, let's go over some technical details. You can listen to the webinar via your computer or via phone call. Details for both were sent out in the registration email. During the presentation, you can post your questions or comments in the questions panel. Please make sure, since we have 3 speakers, to list who the question is for, and we'll address these questions after all 3 presentations. Today's webinar will last an hour and is being recorded. The recording will be posted to the EERI YouTube channel in a few weeks' time. For those of you who may not be familiar, I want to say a few words about EERI. The Earthquake Engineering Research Institute is the leading nonprofit membership organization connecting those dedicated to reducing earthquake risk. EERI has been bringing people and other disciplines together since 1948. By joining EERI, you become a member of our global network of multidisciplinary professionals dedicated to reducing earthquake risk. I want to also say some things about the Younger Members Committee. This committee provides opportunities for early career professionals to advance their careers and become active in the Institute early on. The current co-chairs are Ezra Jampol, Maha Inewi, who is speaking today, and Ashley Morales-Cartagena. A little bit more about YMC. We develop a technical and social meetings for younger members at the EERI annual meeting and throughout the year, such as webinars, the YMC blog. We have a series introducing younger members to leaders in the profession, and we also connect with other EERI committees. Please send us an email or go on our website and fill out the form if you're interested in joining. Today we'll be hearing from Nenad Bielic, Maha Inewi, and Nasser Marafi about their respective research in this area. So without further ado, the first speaker will be Nenad Bielic, who is a postdoctoral scholar at the Unit of Applied Mechanics at the University of Innsbruck in Austria. He received his PhD from Stanford, and his research focuses on dynamics of nonlinear systems and application of statistical machine learning tools. Next up will be one of our own YMC chairs, Maha Inewi. Maha is a postdoctoral scholar at the University of Nevada at Reno. She received her PhD from the University of California at Davis, and her research focuses on assessing the performance of reinforced concrete structures subjected to extreme events, as well as characterizing the regional earthquake hazard and risks to the built environment. And as previously mentioned, she's serving currently as co-chair of the YMC. Our final speaker will be Nasser Marafi, who's a senior modeler at Risk Management Solutions in Newark, California. Nasser received his PhD at the University of Washington, where he studied the effects of large magnitude subduction earthquakes on structures located in deep sedimentary basins. Nasser has received the EERI FEMA NEHRP Graduate Fellowship, the EERI Graduate Student Paper Award, and the UW CEE Charles H. Norris Award. Without further ado, I'll pass this along to Nenad to start us off.
Thank you, Amanda. Welcome, everyone. My name is Nenad Bielic, and I'm happy to share with you today some of the work that I've done in collaboration with Professor Greg Dearline and Professor Teng Lin, and kind of the overarching theme of the work would be utilizing simulated earthquake ground motions to investigate seismic performance of building, and kind of this developed over the years throughout, and kind of stems from my PhD research. And kind of one of the main ideas that we had is whether we can learn something new from simulations, which is not available, say, from recorded ground motions, just to the fact that there's a limited data on recorded ground motions. And one of the key benefits I'll try demonstrating in the next couple of slides. So what I'm showing in the plot on the left is the are the curves corresponding to conditional mean spectra, kind of description of hazard at different intensities. So moving from lower intensities all the way to higher ones, say 1% in 200 years. This for a site in California, and overlaid in gray are the spectra of ground motions, of all recorded ground motions from the NGA West 2 database. And what you can notice here is that at these higher intensities, there's a scarcity of data. So if you want to investigate, let's say, collapse risk of buildings, you necessarily need to scale these motions, and people have worked on methods how to do this. But one thing that simulations kind of enable you to do is to do the same types of analysis, but without having to scale anything. For example, showed on the right-hand side, the same hazard targets, but overlaid with spectra from simulated as part of the SKEC CyberShake project, which I'll mention later on, at the Los Angeles downtown site. And you can see that the coverage is much larger, especially these higher intensities. And note, these are all unscaled ground motions. Since all three of us will be using ground motion simulations, I just thought it'd be good to give a brief kind of higher level overview of different approaches to ground motion simulation, just so you're kind of aware of what is available out there. So on one end of the spectrum are the so-called kind of stochastic models, which described in a nutshell and very crudely. You take a white noise signal as an input, you pass it through a filter, and out comes your simulated ground motion. And now the properties of this filter you determine based, or you calibrate based on recorded motions that you're using. So for the area for which you're interested in, ground motions and so forth. And from what I've just described, it is kind of clear that this approach is empirical, and there's not, so to speak, underlying physics captured with this model. So in that sense, it's limited to extrapolation in terms of the data on which you've done your training of your filter in this case. On the other hand, on the other end of the spectrum, so-called quote-unquote physics-based ground motion simulations, which are essentially based on simulations of waves propagating through three-dimensional representations of Earth structure. And in doing so, these approaches explicitly capture effects of Earth structure, for instance, deep sedimentary basins and their effects on ground motion, which is a huge advantage of these approaches. One kind of quote-unquote limitation of this approach is that these simulations are limited to lower frequencies, for instance, lower than 1 hertz, although you'll see this gets pushed up higher, and there's a number of reasons for this. One aspect is just the computational demand, and other aspects are related to geophysical complexities in terms of resolving the parameters required for the models at the scale you need for these higher frequencies. But nevertheless, engineers, as we want to use these ground motions, we need broadband ground motion. So one way to address this limitation that has been proposed is to use these so-called hybrid broadband simulations, which, put in simple terms, they combine a stochastic simulation at high frequency with physics-based or numerical simulation at longer periods, and kind of splice them together to create hybrid broadband ground motion. And it's these types of ground motions that I have been using. My area of application corresponds to the CyberShake domain, so it's Southern California. If you're not familiar with the region, this is roughly LA downtown, and somewhere around here is the Magic Kingdom. Now, the results that I'll show you in this presentation are based on 20-story buildings. This is 20-story reinforced concrete moment frame, designed in previous studies by Hazelton and Dearline. And this is a ductile moment frame modeled in 2D in OpenSeas with nonlinearities captured with lumped plastic hinges. And kind of the idea is we want to focus our attention mostly kind of on collapse risk. even though the overarching theme is, just very broadly using simulations to learn about performance of structures in maybe areas we don't have much empirical data for, there's a couple of parts to that. One relates to validation effort. In a sense, you can say this: do we trust the simulations, and to what extent? And then if yes, can we use them to learn something new about interesting phenomena such as collapse risk in the basin? And finally, additional aspect that we'll talk about is application of some big data and kind of machine learning tools to just leverage just the abundance of simulations that are available. In terms of validation, I'll just make a plug for a couple of papers on this. And on our part, we were interested in this, for one, to see if we can, to what extent we can trust simulations to move into more interesting areas of application, and also to provide potentially feedback to ground motion simulators. And armed with this more confidence, we then moved into using simulations to explore collapse risk in the Los Angeles basin. And so before I get started, I mentioned the SCEX Cybershake project, where SCEX stands for Southern California Earthquake Center. And it's a project which performs probabilistic seismic hazard assessment by fully using physics-based or numerical ground motion simulations. So if you're familiar with the PSHA project, process, you essentially replace the empirical GMP with Cybershake, and that's how you go about it. This is very high-level overview. For more details, there's this excellent paper. But for the purposes of this presentation, the important part is that for every rupture from the earthquake rupture forecast, let's say USERF 2 or 3, Cybershake generates an associated seismogram. So there's a full waveform that you can use to analyze your structure. So you just don't get intensity measures, you get the full waveform. And this is a huge advantage because it lets you be, more creative in how you do your analysis. So to see this, let's just take a step back and see, how do we use earthquakes, ground motions in earthquake engineering? So conventional approach would be that you start to develop hazard using recorded ground motions. You develop target spectrum, the conditional spectrum, or anything that you like. And then the next step would be you then select and scale ground motions, again, recorded ones, to match that target, and then you run it through your structure. So there's this two-step process which is connected in between or linked by the use of intensity measures. But if you're using Cybershake data, for instance, or that type of data, you can directly go from your rupture to your structural performance without having to use any scaling of ground motions or any intensity measures for that matter. What I just described in figures is shown here in the equation. I will not go through the equations. I will just mention that if you want to do this direct analysis that I mentioned, you have, the way you do it, for instance, we did it for 4 sites in the Los Angeles basin for different reasons. And the way to do it is you need to run your analysis, so run the ground motion through your structure for every ground motion simulated for that site, such that all that collective set of ground motions represents the hazard. In terms of Cybershake, this is about 400 to 500,000 ground motions per site. So for these 4 sites, this required about 1,900,000 nonlinear analysis of the 20-story building that I've shown, which in sequential computation would take roughly 20 plus years. So naturally, we used high performance computing, specifically mostly Sherlock computer cluster at Stanford, which then made it manageable so that we can do one site in a couple of weeks. And what I'll show you next, I'll just get to almost a punchline of contrasting this conventional approach with the direct analysis for the deep basin site in the Los Angeles basin. And again, just to repeat, the conventional analysis is based on using recorded ground motion scaled to hazard targets that are determined using PSHA based on empirical ground motion prediction equations, where this is contrasted to a direct analysis approach using Cybershake data. On the bottom left plot, I'm showing the hazard curves just for comparison. The black one would be the USGS one. The red one is the CyberShake one, so you can see there's differences. But a more striking difference is, you can see on the right, in this comparison of conditional spectra, where the red line, which corresponds to CyberShake, has much larger intensities at longer periods. And this we've observed at a number of intensities. So naturally, this propagates if you do risk fully into risk demand exceedance curves, as you can see them here, or for the purpose of this presentation, in mean annual frequency of collapse, which is about 8 times higher if you compute it using CyberShake approach compared to, state-of-the-art empirically based approaches. For more details, I would refer you to this paper here, because there's a lot of different things that you can do when you have just a lot of data. So you can deaggregate collapse risk and so forth. But one thing that you can say here, well, I was expecting this big of a difference given the difference in conditional spectra that you see. So what we kind of wanted to do next is to investigate the question whether, if we look at the basin ground motions themselves, is there something about them that makes them more damaging as compared to, let's say, non-basin ground motions? And to do this, we extracted a set of ground motions from this, again, deep basin site, STNI, and we match a set of ground motions from a site outside of the basin, this Pasadena site, and we select the sets such that they have matching spectra, which is shown on the left. So the blue is the basin, the red is the non-basin set. They have the matching spectra in terms of means and dispersions, but we also ensure the close match and significant durations. And so the question we're asking, if we have these two sets, one basin and one non-basin, that are nominally identical in terms of recognized intensity measures, is there still something more damaging about the basin ground motions? Just before answering that, as just as a reference, this black line corresponds to the same scenarios as the one selected for the basin ground motion set, but just recorded outside of the basin. So this is what people would typically do previously, compare the ground motion recordings inside the basin and outside the basin, notice the difference, amplification factors, and all of that. But we had a slightly different approach. Again, ensuring that they have same spectra and durations, but do they have different collapse capacities? Shown here is the one example for one specific seismogram that was matched in this way. So the blue one is the basin ground motion, the red one is the non-basin ground motion, and you see the good match in spectra. And if you examine these numbers, close matches in duration. But when you run IDA with these ground motions and kind of compute collapse capacity, the basin ground motion ends up being much more damaging, about 33%. And we see this effect in the entire set as well. Why this is happening? I mean, you could, hand wavy say, well, this is record to record variability, but this didn't satisfy us. So we actually looked into what's driving these differences. For more info on that, look into this paper. But I'll just say that we also noticed this effect in recorded ground motion, so we're working on kind of examining that in the future. And then lastly, the last part I'll just mention is, as I said, we have this data of 1 or 2 million nonlinear response history analysis. So of course, coming from Stanford, you have to use big data and machine learning. And this is what we've done with these kind of data points to see, is there something new that we can learn about efficiency of ground motion, intensity measures, as well as develop tools that enable you to do regional risk estimates very efficiently. And this is something that I'm actively working on. And with this, I would just like to thank you for your attention. This is just an overview of the work that we've done. And this work has been supported by many institutions along the way, which I'm very grateful for. But I just want to finish by saying that the more exciting and more interesting things are yet to come, and you will definitely see this in the next presentation when my colleague takes over. Thank you.
Hi, everyone. Thank you, Ninad, for the presentation. My name is Maha Inewi, and I'm happy to be here today to talk about some of my research at the University of Nevada, Reno on assessing the risk of using simulated earthquake ground motions to reinforce concrete structures. So first, I'd like to acknowledge the project that I'm a part of. The work that I'm doing is funded by the Department of Energy under the Exascale Computing Project. It's a project that is led by Dr. David McCallan of the University of Nevada, Reno and Lawrence Berkeley National Lab. It includes a large team of engineers, geophysicists, and mathematicians and computer scientists. And the project objective is to enable a detailed understanding of the earthquake hazard and risk on a regional scale using high resolution physics-based ground motion simulations that are resolved to high frequencies of engineering interest and up to 5 and 10 hertz in recent runs we've been doing. And I think the difference in this project is that we are using high performance computing tools, and we are using sophisticated numerical models so that we're using a fully deterministic approach over the entire range of frequencies of the ground motions, which is slightly different than the approach Ninad has talked about. First, I'd like to go back a little and talk about the motivation for using simulated earthquake ground motions. Generally, we use simulated earthquake ground motions when we don't have enough observations where we need them. In this particular case, we're interested in ground motions near active earthquake faults. And we don't have enough observations near active faults, and that leads to significant uncertainty in our predictive equations, in addition to limiting our ability to study the unique characteristics of these ground motions and the effects of site conditions and fault rupture characteristics on these ground motions in the near fault area. So the next question becomes, if we are going to use these simulated ground motions, can we convince ourselves that they are realistic? And this is kind of the question that is always underlying the use of these simulated ground motions. And as a structural engineer, I've learned that the knowledge in this field is advancing rapidly, and it's always increasing. And so here I'm going to show a sample of kind of the confidence building checks that we do when using these simulated ground motions. We are looking at here a maximum direction orientation independent response spectra, a comparison between simulated and recorded data set within 10 kilometers of fault. So this is very close to the fault. And what we try to see in these comparisons is, are we capturing the statistical range of variability in these ground motions? And so our comparisons tell us that we're capturing that variability. If we look at the structural response, we also see that we are sampling enough within the statistical variability that we're able to capture the structural response that we see to recorded ground motions. Although we have very few recordings here compared to the simulated ground motions, and here we're looking at maximum interstory drift demand, we see that the median values are close, and we're getting a good range of the variability. So then once we have enough confidence in these ground motions, there are a lot of questions of engineering interest that we can explore. For instance, how does the structural risk vary spatially in a given earthquake scenario? And how do the site conditions and the fault rupture characteristics impact the structural risk? In addition, we can look in detail into what makes these near fault ground motions more damaging and how we can characterize it for engineering risk assessments. So over the next few slides, I'm going to talk a little bit about some of the observations that we see in response to these questions that we try to explore. First, our target region for this project is the San Francisco Bay Area. Today, I'm going to be presenting simulations from an oversimplified domain representing strike slip ruptures of the Hayward Fault. This is run in gigantic, massively parallel simulations in Lawrence Livermore Lab by Arvind Patarka and Artie Rogers. And the domain that we're looking at the surface is 100 kilometers by 40 kilometers, includes thousands of stations and multiple components of the ground motions. And I take these ground motions and then I apply them to reinforced concrete moment frame structures to understand the structural risk. And this is also a highly parallel simulation that I conduct using the Quarry Machine Lawrence Berkeley National Lab in OpenSea's software. So as an output from these simulations, we get these type of what we call structural risk maps, where we can look at the change in the intensity in the ground, in the structural risk. In this particular case, we're looking at interstory drift over the entire domain due to a magnitude 7, for instance, earthquake. And these plots give us a lot of information about looking at the where the structural response is most intense. We're looking here at particularly the fault normal component of the ground motions. And they tell us a lot about the variability of the structural response at different distances from the fault. For instance, if we plot lines along the fault at 1, 10, and 15 kilometers away and create distributions of the structural demands, we see that there is a very large variability over at a particular distance from the fault, specifically for flexible structures. And to give you a sense of the magnitude, we see that the maximum structural demands can vary by a factor of up to 8, 1 kilometers away along the fault length. And so this can have obviously a lot of implications on our structural response assessment, risk assessment studies. We also get an opportunity using these very highly dense simulations to explore the accumulation of the seismic waves as the rupture propagates. In this particular case, we're looking at a rupture propagating from this blue star to the right of the domain. And this is better known as a forward rupture directivity effects and is known to lead to significant velocity pulses in the fault normal component of the ground motion. These velocity, we can study the characteristics of these velocity pulses in the ground motions and how they affect structural demands. Here I'm kind of showing kind of a representation of the deformed shape of the building, and we're seeing that the structural demands kind of increase with the increase in the amplitude of the ground velocity. I'm also showing these kind of measures of plasticity in the structure. These are plastic hinges at the ends of the member that also represent the increase in net plasticity demand. So there's another way to look at that is if you kind of take a perpendicular line to the fault behind the rupture, you see that the structural demands are typically very low despite being close to the rupture initiation. And then as you move in the forward direction of the rupture, you start to see a large increase in the structural demands. And this increase, we see that the maximum structural demands for this type of rupture are typically between 15 or 20 to 60 kilometers away from the rupture initiation, beyond which the demand starts to drop. This also tells us that if we're looking at the fault normal component, then most of the strong directivity effects for this magnitude and type of rupture are seen only within 10 kilometers of the fault. And then beyond that, the demands start to drop significantly. And one important question that comes from the same topic is, what is the potential range of differences between the fault normal and fault parallel component? And this is important because it dictates what type of ground motions we can select for a particular analysis and scale, depending on the site location from the rupture. So for instance, we know that the fault normal and fault parallel component, there are two perpendicular components, very close to the fault, you see that there's a huge difference. The fault normal includes very strong velocity pulses, compared to the fault parallel component. Whereas as you move further away, the two components start to look similar. And in certain cases, we even start to see pulses in the fault parallel component, depending on the rupture characteristics. And so again, this tells us a lot of information about the type of ground motions that we need to pick and scale for engineering analysis. Another source of variability within a particular earthquake scenario depends on the site conditions. In this particular case, we have a basin side and rock side in the domain, almost separated by the fault. And we're looking at a shallow basin, which is different from what Nina talked about, which was a deep basin. But having a uniform distribution of the stations and high density allow us to study the characteristics of the ground motions on either side of the fault and in the basin, on the basin and rock side, very close to the fault. And that tells us that the ground motions on the basin side within 10 kilometers are consistently higher than those on the rock side. And you see that the difference becomes more significant at longer periods. Of course, that manifests in the structural response as well. So if you try to plot, again, a variability at 1 kilometers away from the fault on either side, the basin and the rock side, and the structural demands, you see that the structural demands on the basin side are consistently higher than those on the rock side. And typically the amplification we've seen is higher for flexible structures. Now, as you move away from the fault, we also see that not only the ground motions are amplified, but we see an increased shaking duration. And this increase is typically not as much as you would see in a deep basin, but it's significant enough that it would affect the structural demands. So if you look at two stations 8 kilometers away from the fault, you see that the station on the basin side has about 3 times the significant shaking duration as the station on the rock side. This is manifested in increased drift demands, but also, more importantly, in increased rotation demands, because this type of reinforced concrete structure experiences a degradation. This can lead to a very reduced, much reduced collapse capacity on the basin side as compared to the rock side. Now, another characteristic we look at, the previous slides talked about differences of variability within the same scenario. Now, we don't know exactly how the fault will rupture, and so the different rupture details can have a significant impact on the ground motion intensity and the structural demands. And to kind of look at that, we have 2 types of slip distributions along the fault that we look at. We look at a stochastic slip where the distribution by default of the slip along the fault is stochastic, and the different type of slip where we look at a hybrid slip, meaning that we add these areas of concentrated high slip patches to the fault, which can happen anywhere. We know that for this type and magnitude of rupture, we usually have 1 or 2 slip patches, but we don't know what they would look like. This is sometimes referred to also as temporal variability, because this is going to have in different earthquake scenarios. And our analysis tells us that the presence of these slip patches impacts the structural demands significantly. So we're seeing here that the ground motion intensity is much higher at the same station near the fault between a stochastic and a hybrid slip scenario. And we see an increase of almost 2.5. We also see much higher structural drift and plasticity demands in the structure when we compare these 2 identical stations that are 1 kilometers away from the fault. So this kind of opens up a question for the use of simulated ground motions in general. If we know that their different rupture characteristics will lead to different structural demands, how many simulated earthquake scenarios do we need for an engineering risk assessment? And this is kind of an extensive question that we need a lot of simulations to answer. And you need to consider different rupture distribution of rupture asperities, different locations of the rupture initiation, and other parameters as well. However, in terms of looking at the distribution of slip, we looked at a few scenarios and plotted the distributions again at 1 kilometers away from the fault. And our simulations tell us that the hybrid slip scenarios consistently have higher median demands and variability very close to the fault. And the simulations also tell us that we can place these areas of high slip in regions over the domain or over the fault plane so that they lead to more conservative estimates. So kind of the preliminary answer is we probably don't need a whole lot of simulations. We probably just need to determine where the locations of the rupture asperities that lead to more conservative estimates of the structural demands. In this case, we know that when we place them closer to the fault, to the rupture initiation, then we see higher structural demands, in certain cases higher variability. However, this is a question that we're still exploring. It needs a lot of analysis. So in summary, much of the uncertainty in designing structures to resist earthquakes comes from our limited knowledge of earthquake loading. And so physics-based ground motion simulations, they give us an opportunity to understand the variability in the earthquake hazard and risk, particularly near active earthquake faults where we don't have enough observations. These simulations can offer insight on understanding the impact of fault rupture characteristics and side effects, and also characterizing the characteristics, the properties of near fault ground motions, so that we're able to incorporate these properties into engineering risk assessments. And finally, the goal of using these types of simulation is eventually we can improve the ground motion prediction equations and our structural design guidelines for near fault analysis, particularly selection or scaling of recorded ground motions. Thank you, everyone. I will hand it over now to my colleague Nasser Marafi, who will talk to you about his work on simulations of the magnitude 9 Cascadia subduction zone earthquake.
Thank you, Maha. Hi, so my name is Nasser Marafi. Today I'll be talking about the effects of simulated magnitude 9 earthquake motions on reinforced concrete coral wall structures in the Pacific Northwest. So this work was actually done while I was a postdoc and PhD student at the University of Washington. And so I'll start off by just providing the audience of some of the motivation behind this work. So the seismic hazard in the Puget Sound region includes large magnitude earthquakes due to the Cascadia subduction zone. Earthquakes along the fault rupture have about a 500-year return period, and the USGS estimates that there's about a 10% chance of this occurring in the next 50 years. Motions are expected to be long during this type of earthquake, yet current design codes do not explicitly consider the effects of duration on structures. In addition, a lot of the structures in the Puget Sound region are overlying a deep sedimentary basin that is known to amplify ground shaking intensity. And this effect is also not considered in the seismic hazard calculations considered in the code. We also don't have recordings for this type of earthquake, and so our understanding of how buildings are going to behave during this earthquake are poor. So I'll start off by speaking about how we plan on addressing the paucity of M9 recordings in the Pacific Northwest with the use of physics-based simulations. I'll then move on to talk about the characteristics of the ground motions produced during these simulations. And then the last half of the presentation, I'll talk about the impacts and what these simulations mean on the performance of mid-rise and tall reinforced concrete wall structures. Before I begin, I'd like to acknowledge that this work was part of a large collaborative research project at the University of Washington and the United States Geological Survey. This work would have not been possible without the help of my co-authors, Dr. Jeffrey Berman, Dr. Mark Everhard, and Andrew McDeesey. I'd like to also acknowledge the financial resources that were provided by the National Science Foundation, USGS, EERI, and ATC. And I'd like to thank DesignSafe for their generous computational resources and the scientific input from numerous researchers on the M9 project. So the physics-based simulations were headed by Art Frankel and Aaron Worth from the USGS, where they simulated 30 realizations of a magnitude 9 earthquake. Each realization had varying rupture parameters, such as the location of the hypocenter, the rupture depth, the slip distribution, among many other parameters. And each scenario used a seismic wave velocity model of the Cascada subduction zone, which includes several deep sedimentary basins in the region. High-performance computers were then used to generate deterministic motions with period contents above 1 second. These deterministic motions were then combined with stochastically generated motions with frequency constants below 1 second to create broad bands across a 1 by 1 kilometer grid in the Pacific Northwest. So here are two scenarios of a magnitude 9 earthquake with a hypocenter just off the coast of Washington. Realization 1 on the left is a hypocenter rupturing towards Seattle, and realization 2 had a hypocenter just off the coast of Washington but rupturing away from Seattle. And what you start to notice is that the two realizations are actually of a magnitude 9 earthquake, yet they produce different ground shaking time histories. The one in Seattle appears to be much more intense. So here you can see this again using the velocity time history for Seattle for the two realizations. And if you look, you start to see that the amplitude between the two scenarios are different, where the rupture towards Seattle has a larger amplitude than the realization away from Seattle. If you look at the wiggles and the spacing of the wiggles, you'll start to see that there's also differences in frequency content. Now, structural engineers have found ways to quantify both amplitude and frequency content using a response spectra, which we can then use to estimate the engineering demand on structures. So here I'm plotting the response spectra for the two scenarios on the y-axis, and on the x-axis, the period of the oscillator. And the spectral accelerations that you see between the two scenarios are quite different. For example, if you had a 20-story structure with about a period of about 2 seconds, and let's assume that it has a strength about 50% of its mass, then what that means is that in the realization where you have rupture towards Seattle, that structure would deform inelastically and start to see some damage. Whereas if you had the realization where the rupture was away from Seattle, that structure would deform elastically and return to its original state after the earthquake is over. We wanted to quantify the effects of a magnitude 9 earthquake probabilistically, so we actually simulated 30 realizations. And here you can see the response spectra for all 30. And what you can see is that there's actually quite a large variation in spectral accelerations between the realizations. And this goes back to the variations in rupture parameters that Maha was presenting. Shown in red here is the maximum considered earthquake, which structural engineers would use to design structures. And what you start to see is that there's a lot of realizations that exceed the maximum considered earthquake used in Seattle. For example, at 2 seconds, we have about 20 out of the 30 realizations that exceed the MCE spectral ordinate. One reason for this is we think that because basin effects aren't considered in the seismic hazard calculations, the spectral accelerations that we're seeing from the simulations exceed that we're using in design. Another interesting characteristic that we found is that there's quite some regional variation in the motions. And so these time histories are for Seattle. If I go 80 kilometers south of Seattle while maintaining a similar distance to the fault rupture plane, we saw that the shaking intensity was quite lower. Now, if you were to talk to any seismologist or ground motion modeler, they would say that they would expect similar shaking intensities between the two locations if they had similar site properties, and we weren't seeing that. We can see the same thing again if we plotted the response spectra, where the spectral accelerations in La Grande, Washington were actually much lower than that of Seattle. Now, we believe the differences that we're seeing here is due to basins, and one way to measure whether or not you are in a basin is to measure the Z2.5 parameter. And this parameter is just a quantitative measure that takes the depth from the surface of the site, from the surface of the site to a depth to where the crystalline rock has a shear wave velocity of about 2.5 kilometers per second. So if you're in the deep part of the basin, you'd expect this distance or this Z2.5 parameter to be large. If you're in sort of the outskirts of the basin or outside of the basin, you'd see that this Z2.5 parameter was quite small. And so here I'm plotting the Z2.5 as a contour map, and what you start to see is the shape and size of the basin. And Seattle happens to be in areas where Z2.5 is actually quite large, where it's around 7 kilometers. Whereas La Grande, while it has a similar source to site distance, it has a much lower Z2.5 value of about close to, actually outside of 1, so close to 0. Another important ground motion characteristic is the frequency content at longer periods. This is important because under strong shaking, our building is going to deform and inelastically, and that causes the period of the structure to yield and its period to elongate. And so what happens, the frequency content at longer periods than the elastic period starts to affect the response. And so if we go back to the response spectra, we can start to see that there are variations in the spectral shape between the realizations. For example, if we had a 0.5 second structure, and this structure yielded in both of these realizations, in realization where the rupture is towards Seattle, we would expect the building to see a much different response, a much more damaging response than in the realization where the rupture is away from Seattle. We also saw that the simulated motions have long durations, which is what you would expect from a large magnitude earthquake. And when we compared this with motions measured during crustal earthquakes, we noticed that they're actually much longer. And so, and many researchers have found that long duration earthquakes cause the structure to go through more cycles and start to accumulate more damage. And so thus far, I've showed that the M9 simulations that we've had produced high spectral colorations. In some instances, they've produced damaging spectral shapes, and they have much longer durations. So the next question that I wanted to look at is, what this means for structural response. And so to answer this question, we wanted to analyze a set of structures that were representative of those designed and built in Seattle today. Therefore, we worked with the city and many of the engineering firms to develop structural archetypes that we can study. So to understand the effect of the simulations, we looked at a range of buildings with varying number of stories from 4 to 40. These buildings were sort of representative of high-rise residential condo buildings with fixed story heights of about 10 feet and a fixed floor-to-floor plate. The buildings had a lateral force resisting system of a central core that was coupled in one direction and uncoupled in the other direction. The buildings also had up to 4 levels of basement levels. For all the archetypes we've built numerical models using OpenSeas so that we can simulate the response of the building under strong shaking. So for each of the archetypes that we had, we subjected them to the M9 ground motions. And then for each analysis, we measured engineering demand parameters like maximum story drifts and the rotations. And using that, we tried to predict the amount of damage that each archetype would see in that realization. And then finally, using the results from these analyses, we would predict the likelihood of building collapse. Here's an example of 2 buildings subjected to the 2 M9 motions that I showed previously for Seattle. The left animation is the rupture towards Seattle. The right animation is the rupture away from Seattle. And the contours that you see here represent the strain that the concrete and steel go through under the earthquake. The darker regions that you see right here just indicate areas where the concrete core has yielded. And the colored circles that you see here just indicate the likelihood of the gravity system connections failing. And what we start to notice between the 2 realizations is that the damage varies between realizations, even though both are of a magnitude 9 earthquake. Before we looked at the results from the M9 simulations, we wanted to compare the performance of these archetypes with ground motions that represent the hazard computed from empirical relationships like ground motion models, and then compare the performance of the simulations to that from recorded motions. So to do this, we selected and scaled numerous ground motions to represent the seismic hazard in Seattle using a multiple stripe analysis. We then subjected all the archetypes to these motions and computed a collapse fragility function that I'm showing here on the left. We took this collapse fragility function, integrated it with the hazard curve to compute the annual rate of collapse, which then we translated to a 50-year collapse risk. And so what I'm showing here is the 50-year collapse risk for all these archetypes. I'd like to preface first by saying that the building code does target a 1% chance of collapse in 50 years. And so what we noticed is that if you used motions that were selected to match a seismic hazard that did not consider the effects of basins, you were generally below that 1% chance of collapse. The minute you started to select motions using a seismic hazard that included the effects of basins using the ground motion basin terms available, that collapse risk increased to about 1.9%. So about just under double the target. Now, all of these motions don't use any of the physics-based simulations. So next, we wanted to figure out a way of trying to use the physics-based simulations by first computing the collapse risk using ground motion selected to represent all hazards that were not large magnitude earthquakes. And then we computed the annual rate of collapse, so the collapse risk from just large interface earthquakes. So all the physics-based simulations. So essentially, we just replaced all the ground motions that were associated with large magnitude earthquakes with ground motions that were simulated. And then we computed the collapse risks for the two and combined it to compute the 50-year collapse risk. And what I'm showing here is the collapse risk considering simulated M9 motions and basin effects. And what we start to notice is that the collapse risk increases to about 2.6%. So this increase that you're seeing in collapse risk is really attributed to characteristics of the ground motions that I previously presented in the first half of the presentation. Now, these characteristics are not necessarily reflected in the ground motions that I've chosen and scaled and selected to represent the seismic hazard here and here. And so to conclude, I've shown today that the simulated magnitude 9 cascaded subduction zone motions are damaging because they have large accelerations, they have damaging spectral shapes, and they are long in duration. The building code targets a 1% chance of collapse in 50 years. If you used a seismic hazard that did not account for basin effects, you generally met that criteria. The minute that you included basin effects, the collapse risk almost doubled. And if you included the physics-based simulations in the seismic hazard calculations, that collapse risks went to about 2.6%. And so next, I'd like to thank everyone for listening today, and we welcome any questions that our audience has on all three presentations.
Thank you, Nasser. I think we can move on to the Q&A portion now. For those who weren't logged on at the beginning, please just submit your questions here. We have some to start. We'll start at the beginning. I have a question for Nenad from the listeners. Can you please speak to the limitations of the hybrid broadband ground motion simulation approach in terms of its effect on the structural response?
Yeah, thank you. That's a great question. So essentially, what is the kind of the range of structures that you would want to examine, either you can kind of quote unquote reliably examine either by just physics-based ground motions or hybrid broadband simulations? And we did do some work along those lines. I mean, the answer is pretty, what we kind of found is what we were expecting to begin with. When you're using these hybrid broadband simulations, there's this splicing period, which is the period or frequency at which you're combining. Below that period is the stochastic portion, above that period is the kind of numerical physics-based component. And let's say, then it depends on, the fundamental period of your building, whether it's above the splicing period or below the splicing period, and also whether, the EDP, the engineering demand parameter that you're looking at, is susceptible maybe to higher modes, and whether your structure has, let's say you're building the first 3 modes, let's say, control the most of your response, both in terms of, say, drift, but also accelerations. If all 3 are in the physics-based domain, so to speak, then if you take the hybrid or just the physics-based version of that, so without the stochastic component, you don't necessarily see the difference between them. But as soon as you start moving in this region, that some of the modes are in the stochastic part, some are in the deterministic part, then you can see pretty large differences in mostly these demands that are controlled by higher modes. But this is one of the reasons, and this is a contentious issue, so I don't have a definitive answer, but it is one of the points why we steered clear away. We wanted to have our structure with the fundamental mode far enough, so to speak, from the splicing period, such that we're kind of not being affected by those effects, so to speak. Yeah, but I hope, yeah.
All right, thank you. Next, I have a question for Maha. Could you please give a hint at the impact of your near fault work might have on design codes? Might you have a specific proposal based on your work?
Yes. So there actually, as I mentioned, there were a lot of questions that we're looking into. Most importantly, we're interested in looking at the variability very close to the fault. And one of the things that I'm interested in doing is comparing how this variability compares to what you would get, the variability you would get if you follow the probabilistic seismic hazard conventional approach, or even, a more closer to the code approach. And this can give us an idea of whether we're close to what we would see in a probabilistic seismic hazard analysis, or if we're missing some components of the variability. And I think this could really be an important part of the equation, because if we're looking at collapse capacity, we're always looking at distributions of structural demands, and we want to know both the median capacity and the variability. And so this variability factors really heavily in our assessment of our structural capacities. So knowing the variability, I think, and comparing what we see using the simulations as we get more and more confident in the simulations, and comparing that to what we see from probabilistic seismic hazard analysis will give us an idea of where we are, and will help us improve our design characteristics. Another area actually we're looking into as well is we don't have a lot of near fault recordings, so we're not confident in the characteristics of the pulse ground motions that we see. These are ground motions with strong velocity pulses, and we don't know, but there's been a lot of work on this over the past few years, but there's still some work to be done understanding how they affect the structural response in the near field, and what types of structures are most sensitive to these ground motions, and how the change in their frequency content affects the structural response in the near fault. And this will also have an impact, I think, on the design, because it would guide us to select particular ground motions for engineering analysis rather than others, because you want to make sure you're picking, you're selecting for your analysis ground motions with the right frequency content that will give you reasonable structural response distributions and demands that you're expecting to see at your site.
Thank you, Maha. Moving on, I now have a two-part question for Nasser. So part one is, could you please comment on the basin edge effects and its impact on the structural response? And part two is, if the Seattle Basin was much shallower than Z1, how would the simulation validation process change?
So, the response spectra in Seattle that I've showed does include basin edge effects, but it also includes sort of amplifications that you get due to the lens-like shape of the basin and the contrast of shear wave velocity structure between rock outside of the basin or just below the basin and rock inside of the basin. And so it's all lumped in there. Seattle is sort of in the middle of the basin, so you see amplifications from all of the three effects, which include basin edge effects. Can you repeat the second question?
Sure. If the Seattle Basin was much shallower than Z1, how would the simulation validation process change?
So Z1 and Z2.5 are proxies for basin effects and or proxies for basins. And so in Seattle, we typically like to characterize our basin using Z2.5 just because I'll give you a brief history about the history behind the Puget Lowland basins. There was, thousands of years ago, there was the ice age that sort of compacted a lot of the till that you see in Seattle. And so if you dig a couple of meters just below soil, you'll hit this really hard till that tends to have shear wave velocities of about 500 to maybe 1,000 meters per second. And so our Z1.0 values in Seattle are actually quite low compared to other regions, but our Z2.5 values, so the depth to rock associated with 2.5 meters per second, are actually quite large. And we believe that a lot of the basin amplifications that we're seeing is due to that stiffer rock being so far below the city.
All right, thank you, Nasser. I think we're running close on our time, so I think we'll move ahead to wrap up, but please don't hesitate to reach out to me or any of the speakers with follow-up questions. We hope you enjoyed this webinar, and before we end, we want to share an upcoming webinar with you. So the EERI Professional Development Committee will be hosting a webinar titled A Multidisciplinary Approach to Improving Community Resilience to Natural Hazards on August 26th. If you're interested in attending this webinar, registration information will be included in the follow-up email you'll receive shortly. Thank you all for attending this webinar. PDH information will be provided in a follow-up email. Please also complete the webinar survey to provide your feedback. If you're not already an EERI member, please see the follow-up email for more information about how to join, and the same goes for also joining the Younger Members Committee. To find out about upcoming EERI webinars, please check the EERI Pulse newsletter. And finally, we thank FEMA for supporting this webinar, and thank you to the 3 speakers today.
Thank you.
And thank you for your time.